It's 8:30 and 10 seconds. Let's start our morning session. I'm the chair for this morning, Lynn Heller from BIMSA here, and I'm happy to announce Mihai Paun from the University of Bayreuth in Germany, somewhere in Bavaria, in case people don't know.
How could they not know?
Wagner Festival is very famous around the world.
Sure.
Okay, he will talk about Hermitian Yang-Mills connections on log terminal Kahler spaces and applications. Let's welcome him.
Well, thank you, Lynn, for the introduction. And I would like to thank the organizers for the invitation. It's, of course, a great pleasure and honor to be here in such a wonderful place, in such good company. And like everyone, I'm very impressed to see so many nice lectures at the same time, to the point I would like to be in many, many rooms simultaneously, but that's maybe not so much possible. So actually, the main theme of my, the keyword of my lecture would be somehow applications. What I would like to present today is the ways and some recent results due to Fong and his collaborators can be used in order to study the geometry of KLT, Kahler spaces. So as an example of that, I took by randomly 2 papers. In which by one of the co-authors. So the first one is with my former colleagues in Bayreuth, the long list of people. And then, as David here pointed out, I still remember that W is is after G in the alphabet, but so this is supposed to be my co-authors with the first and the second paper. So let's get started. This is somehow what you will see in the next few moments. So as a preliminaries, let's start like all nice good stories with the compact Kahler manifold and the vector boundary on it of rank R. And then I of course don't have to remind you what is stable, but still I put it on the slide. So so E is stable with respect to the metric omega. If for any coherent proper subsheaf of E, we have this slope inequality, right? So the slope is the one that you know, the degree of the subsheaf divided by its rank. And now, so as they say, one always has to start with a very classical result, and the very classical one would be this one. So the following theorem. If the boundary is stable, then it means a very, very interesting metric on it. Namely, this Hermite-Einstein equation is satisfied. The contraction of the curvature form with respect to the metric is a multiple of the identity, right? So Narasimhan was for the case of curves, and then Donaldson in the projective case. And finally, the result, which will be particularly relevant today, was established by Uhlenbeck and Yao in the context of compact Kahler manifolds. Please. Who? So the theta is the curvature. So this is the curvature form of the E, and then you contract with omega, and you get some multiple of the identity. Excuse me? The converse is absolutely true, provided E is irreducible. So intercomposable. If you have such a metric, then E is so-called polystable. So now, as a consequence of this, if E is stable, you have a very, very interesting Chern class inequality, the Kobayashi-Lübke, between C2 and C1 squared, which is the one here, and which is very, very useful and particularly relevant for the rest of my talk. And somehow, what I will try to explain in what follows is I'll try to formulate and give you a hint about how it's proved the analog of these results in somehow in a singular setting when we replace our beautiful manifold X with aggressive normal compact Kahler space and E with a torsion-free coherent sheaf. Now, this is not just a generalization per se. I will explain somehow what was the main motivation for me to get interested in these topics. So let's see. The first thing to agree about is what would be a metric on a coherent sheaf, because there are many competitors there. So let's see. So the convention that we took here is the following. So X, like I said, is a normal complex space. And then, so by definition, now a Kahler metric on X is given as follows. So we have X as a union of, if you want, trivializing open subsets, so that A alpha is some analytic space in Cn. And then by definition, omega is written locally as DDC of some strictly smooth and strictly subharmonic function, which comes from the ambient space. Okay, so omega in this talk will always have local potentials coming from the embedding, from the local embedding. So this was somehow the notion of Kahler space introduced by Glauert. And then now, given a coherent sheaf on X, so locally we have this. This is given by this exact sequence. And then let's assume, moreover, that F is torsion-free. So then outside codimension 2 is as good as a vector bundle. And let's say that R is the generic rank, so that is to say the rank of this vector bundle here. And then, yeah, so now my definition of a metric on F is simply to take the sequence that we have. Now, let's see, where's the pointer here? Maybe this one? So we take, we take this sequence, we take the trivial metric here on this locally free sheaf, right? And then we have quotient metric induced by F, right? So this is of course only defined on where it's possible when it's a vector bundle, but still it's perfectly well defined at each point of this open subset. And then we globalize this by a partition of unit, okay? I mean, it seems to me that, yes, but this is somehow too liberal for what I'm trying to explain next, because you will not know what's happening near this guy, and that's somehow my mm-hmm. So I'm trying to say that as we get closer to the singular loss of the sheaf, that metric has a very well prescribed behavior. It is the quotient metric induced by this. Okay, you could simply say I take a metric or whatever metric in the complement of this set. Okay, but then you will not know what's happening at infinity. This one tells you. This one prescribes that. This is somehow the motivation. Now, I computed an example for you, a very simple one, of course. So let's say that F is this sheaf here in C2. And then, as we know, we have this resolution, right, by two terms in O square and O, given by these maps. And then the metric has this behavior. If we take, for example, this section as 1, the norm of the section in question is Z1 squared divided by the sum of the squares of the coordinates. Fine. A very good exercise. Now let's get closer to the main theme of the talk. So if we have an analytic set in general here, I took the singularities of X and the singularities of F, put them together and call this Z. Then we can construct a metric, construct a function, phi z, which has logarithmic poles along this subset. So the fi's here are the local equations of z. Yeah. So yeah, I wrote it, of course, locally, but then you can globalize this again, and then call that phi z. And then in this context of a coherent torsion-free subshift, then the slope it's still well defined, right? So even if you integrate only on the regular pipe part of x, it's basically due to the fact that this guy is torsion-free. So outside for the codimension 2, you don't have any troubles. And then let's denote x0, the open part. So where you remove basically everything. And then the first result I would like to explain is the following. So if this object is stable and coherent torsion-free on a normal Kahler space X, then we can construct a metric, which call it HF. So HF0 is the metric that I defined before, right, by using the partition of unit at local resolution. And they differ by some endomorphism, the exponential of some endomorphism of F. So again, this is only defined by on the open part, and it has the following properties. It is smooth and satisfies the Hermite-Einstein equation or x0, so it's our candidate for Hermite-Einstein metric. But moreover, we know a little bit what's happening when we get closer to the singularity. So we have some estimates which tell us what's happening when we get close to this loci here. So we have an upper bound for the trace of the exponential of this morphism. So all the eigenvalues are bounded from above. Now the bounded from below is not as glorious. So the exponential of S is only bigger than some multiple of the sum of the equations eventually to some high power times the identity. Okay, so can eventually degenerate where we have singularities. So I don't know. Of course, my dream theorem would be to have a constant here as well, but for the moment, that's what we can do. You will see in a moment why. Okay, so we have this, and then the usual thing that we have some estimates for the L2 norm of the derivative of this S, and more importantly, the curvature is L2. So here is one of the somehow key point of this whole story. Curvature is L2, but in general, not L2 plus epsilon. And this would be really good to have it, the epsilon, the additional epsilon there, but in general, the geometry only gives us L2. Very good question. I have no idea. Yeah, most likely yes, but I haven't considered the question yet. Fine. So now people who work in this direction, well, I think the first one to consider this sort of context were Bandel and Siu. In the work, X was non-singular and F was coherent torsion-free sheaf. And then many people, among the recent ones is Chen and Wentworth. So I will not try to give you the whole list of people because if I ever forget somebody, he will instantly become my mortal enemy. So I won't want to risk that. And yeah, so let's see now what will happen in the rest of the talk. I will explain to you somehow, try to explain to you what's inside the proof of this, and then what was the main motivation. Fine. So we will proceed by the so-called desingularization of sheaves. So we recall the following result, which was established by Rossi in the late 60s. So there exists a map like this, which from x hat to x, which does the following for us. So turns x here into a compact Kahler manifold, and then along the smooth parts of X and F is an isomorphism. Then does something else, is that the exceptional divisor is has simple normal crossings, so it's particularly nice. And most importantly is that the pullback of F modulo torsion is the locally free sheaf, so it's a vector boundary. Okay. Now, what are the consequences of Okay, so before the consequences of that, so let me make the remark that the stability is preserved by this operation. So the hypothesis that we have turns into a stability of E, but with respect to this pullback of omega, which is not calorimetric, right? It has zeros. And then now, as we know, it's important to know results, but even more important is to know proofs of the results. So as the consequence of the proof of Rossi, what we can say is the following: is that the metric that we constructed, it induces a smooth metric on this one automatically. So so this is another motivation. So for concerning with respect to what Florin asked, is that we get this somehow automatically from the proof, that the way these objects are constructed. And then moreover, we can compare the norm of the sections. So we have, if we have a section of F downstairs, we take the pullback, and then we have uniform constants here, right? So those constants are not going to 0 or infinity as you approach the exceptional divisor, okay? And then, so as a consequence of that, and the fact that we are taking the so-called quotient metric, we get an automatic, we get this handsome lower bound for the curvature of E with respect to this specific metric that we have here. Namely, is bounded by some negative constant times the inverse image of omega times the identity. Okay, so the usual thing, if you take some arbitrary metric, you'll have to replace this one with a Kahler metric on X hat. But as a consequence of our construction here, we get something which comes from the base, right? So on contractible subsets of this map, E is automatically semi-positive. Okay, so again, this is the consequence of the fact that we take the quotient metric, and as we know, by quotient, the curvature increased. Yeah. Fine, and then so what I would like to say now here, we are trying to solve a problem which is on singular space. Now, in general, there are two methods of doing that, either by approximation. You approximate your object with some smooth ones and then try to take the limit. Or if you have a good understanding of how your singularities they look like, for example, if they are quotient singularities or if they are particularly nice, then you can try to cook up some to adapt the objects that you work with and then prove the results in this setting. Like, for example, it was done by Somsun, Hein, and Gabo, Sekeridi, and many other people. But here we are working in a very general context, so we will proceed by approximation. So what's the story here? So we take a metric on the omega x hat, like that. And then we can choose the epsilons here in such a way that this is a Kahler metric. That's very well known. And then we perturb our inverse image like that. Some small multiple times this omega x hat. And then by miracle, this becomes a Kahler metric now on space. Now, there's a lemma saying that the boundary is still stable with respect to this perturbed metric. Right? So it is stable with respect to the inverse image, but then if you perturb it a little bit, or t smaller, very, very small, then it's continue to be stable. And then from this point, I think it's clear what we want to do. So by Ulebeck-Yau theorem, so we get a family of Hermite-Einstein metrics on E in such a way that this equation is satisfied with a square root of -1, which I forgot. And then what we want to do is, of course, to take the limit as t goes to 0. So what I will explain to you next is how can we do that. Now, let's consider the determinant of E, and then theta L would be the induced curvature form. And then we can solve the following equation, right? So the Laplace of rho, this is our solution, plus the contraction of this curvature form is the right constant, so that's the integral of this guy is 0. And moreover, we can normalize rho t by this condition here. So then the metric that we introduce here, HT0, would be somehow this will play the role of our reference metric for the parameter t, right? So if you remember how you do how you prove the existence of Hermite-Einstein metrics in the usual situation, you always start with a metric for which the determinant is already Hermite-Einstein, and that's exactly what we do here. And then our solution, for each t, for each t can be expressed as follows. So it's our reference metric times the exponential of some endomorphism. But now the advantage is that we have the trace of this endomorphism, which is 0. Fine. So then now, of course, the goal would be to take the limit as t goes to 0, and then try to argue that the limit will be our metric in theorem 1. And of course, the main difficulty is to analyze the geometric invariance of this family of Kahler manifolds, right? They have to be reasonably bounded in order to take limits, right? That's what we have to try to convince you that we have a reasonably good control of this family of Kahler manifolds, so that the limit exists, makes sense. So for this, let's try to see what we have. Who are our allies in this story? What are the uniformity properties of the family? Well, of course, on compact subsets in the complement of the exceptional divisor here, everything is very nice because omega downstairs is a Kahler metric. And then, of course, this omega t is bounded from above by some multiple of the Kahler metric on x hat. That is absolutely immediate given how we constructed omega t. But then let's see some more of those. Now, if x is non-singular, the Sobolev constant, which is one of the main players in this story, is bounded, this is independently of t. And in general, this was only established very, very recently for this family of metrics here. And I will explain to you why is that. So here GPSS stands for Guo, Fong, Song, and Stuhl, the Rutgers team. Yeah. So now let's look at the following expression. So omega t to the power n, which can be developed like this. And then we set ft, which is the log of the omega t to the n divided by the determinant of omega x hat. And then what we see is that this ft, well, at least locally, is bounded by this expression here, where the functions that we have are holomorphic, and the first one is not identically 0. That's the case because the first one corresponds to the Jacobian of the map, and that's has zeros, but is not identically 0, okay? Wonderful. So it follows that this quantity, which is called the p entropy, is bounded for any p positive, okay? So at least we have this sort of information about the entropy. And then now, like I said, one of the main difficulties in this story is to control the Sobolev constant. Now, the Hermite-Einstein equation looks like a generalized Laplace equation, right? So in order to analyze that, what you need is the green kernel, some information about the green kernel, right? Which is, as everybody knows in geometric analysis, if one managed to control the Sobolev constant, then you have a good understanding of that. Now, here the Ricci curvature of this family of manifolds is not bounded as t equals to 0, and the Ricci curvature usually gives you information about the Sobolev constant, as we know. So we have to somehow manage to say something without the Ricci curvature. And this is exactly where we got super lucky because of the work of these people, Wolfram and Sturm. So what they prove is the following. So for this particular family of metrics, that is to say the relevant property is that the entropy is bounded. You have the so-called the following mean inequality. So for any C2 differentiable function on the set v greater than -1, such that the Laplace is bounded from below by some constant, then we have that the supremum of V on x hat is bounded by some constant which is universal enough. And for us, what's really relevant is that independent of t plus, well, 1 plus the L1 norm of V. Okay. So again, if you have some information about the green kernel of omega t, this is absolutely standard. But like I said, green usually is controlled by using the Ricci curvature. And then these people managed to prove the sort of inequality here without any information about Ricci. This is exactly what is somehow the main technical tool. So yeah, in particular, the uniformity of subordinate constant here is not required. It's just a matter of controlling somehow the cohomology class of omega t, which is bounded, and the entropy, which is good as well, as I explained on the previous slide. Now, so a comment about this result is that the hypotheses under which it holds are really very, very flexible. And then which is more important and agreeable and nice is that this fit to our geometric context. So I was very happy to see this appearing. Now, yeah. Somebody twist my arm to read it, and I did. So yeah. So now let's see how we get estimates for these components of the Hermitian metric by using this result. I realize that it's difficult to read on slides and so early in the morning, but I'm just trying to give you somehow the rough idea. So let's see how we get estimates for the scalar part of the metric. So recall that we have this inequality here. The curvature is bounded from below by somebody coming from the base times the identity of E. And then the notation was like this. L is the determinant with the induced metric, and then rho was a function which verifies this equality here. And then we have the following lemma: is that there is the positive constant such that rho is bounded from below in a universal manner by a constant which is independent of t times the L1 norm, and then the upper bound, it depends on it somehow degenerates logarithmically when we get close to d. But still, we have uniform constants all the way. Now, just one line about the proof is that now if we take the determinant here, what we see is that well, the curvature of E is bounded by some constant coming times the metric coming from x, and this is greater than some constant times omega t. So omega t, it degenerates, but still is bigger than the inverse image of omega. And then by taking the trace, well, what we get is that well, the trace is with respect to omega t is greater than some constant. And then happy we are, because from this equation here, we infer that the Laplace of minus rho is greater than some universal constant. So that's exactly how we apply this result, the GPS. And then now you will see why the upper bound is not as good. It's simply because the upper bound of, so this is a smooth metric after all, so it's bounded by some constant times the metric on x. And this one is expressed like that, right? If you look at the formula I wrote a few minutes ago, that's exactly the expression of the metric here, of course, in the complement of t. And that's our metric omega t plus this guy here. And then, well, smaller than this. So then again, this time that the trace of theta is smaller than 1 plus the Laplace of the logarithm of that. So that if you incorporate this inside the Laplace, then what you get here is a uniform lower bound. But of course, this guy is singular. Never mind, the result of GPS still applies in this situation because it's C2 outside the singularities. So we get the result, right? So from this we get this part of the lemma. Now, as usual, the estimates for the endomorphism are slightly more complicated, but they go in around the same ideas. So what is happening is that the Laplace of the log of the trace of endomorphism here is greater than this quantity. Now this is absolutely standard in the Hermite-Einstein theory. So this is the analog of C2 estimates in Monge-Ampère, right? So we apply it for each t. So everything depends on t. It's terrible, but still. Recall that the curvature form here is bounded by this expression. So all in all, what we get again is that the log of the trace of our endomorphism is greater than some constant, and then again it follows that the logarithm of the trace is bounded by this. So the upper bound, pointwise upper bound, is smaller than some constant plus the L1 norm. Okay, so then the heart of the matter is to get constants which are independent of t. And then somehow the main step in the proof of theorem 1 is the following, is theorem 2, wonderful. So that there exists a constant such that this trace is smaller than c and rho is bounded like that. And the proof of this, so if you remember, and of course you do, the proof of the yes, so they only depend on the, if you want, on x and omega, together with the some other quantities, but the main point is they are independent of t. This is what is relevant for us here. And then so, for example, if you read the proof of the existence of Hermite-Einstein matrix in the paper by Simpson, what you see is that as soon as you have this sort of inequalities here, the rest is somehow standard in the sense that so you argue by you prove such inequality by contradiction, and you eventually produce a destabilizing sheaf if they fail. But so somehow this is rather non-standard in the sense that omega t varies, but still the main steps of the proof are the same. So somehow this sort of inequality here is what was to be done combined with the usual arguments. Fine. So I will stop here with the theorem 1. And then let's go a little bit farther, and then let's see. So for the moment, we only considered a space which has, which is a normal Kahler, compact Kahler analytic space. Now let's say something about the following more refined somehow situation when you have so there is some set of codimension at least 3. Such that in the complement you have the singularities are at worst quotient. Right? So the locally at each point of the complement of this high codimension set, you know that you have neighborhoods which are quotient of open subset in Cn modulo some finite automorphic group. So this is what is happening, for example, if X has so-called KLT singularities. And so here, let me, so this is an example, well, to the fact that maybe the metric we are considering usually on these spaces, well, it's not maybe it's not the right one in the following sense. So let's look at this very simple singular set where you have C2 modulo plus minus the identity. And then the following map embeds X into C4, right? So the first coordinate is fixed, and then you have this u square uv and v square, and then so the Euclidean metric restricted to x0, which is exactly what we took, looks like that in respect to these coordinates, right? So it's not positive, right? That's what we see. That's what we steadily realize. And then, but the natural metric would be simply this, right? Because this pullback via this map would be Euclidean, right? So this would be the so-called orbifold metric on our space. And this one is simply the Kahler metric, the non-singular Kahler metric that we took. Okay, so somehow what I'm trying to say here is that this one would be much more useful than the one we have at hand. So now let's assume that in the complement of this high dimension set, our sheaf F has this additional structure is induced by a vector boundary. So this just means that when you restrict F, let's say to the loci where it's a vector bundle, this can be extended to a vector bundle on U. Well, this is the technical way of expressing it. And then let me just say that such a context is natural in birational geometry. So now what we would, let's assume that F is omega stable, and let's assume that X has this sort of singularities, right? So outside some high codimension set, everything is very simple. So on quotient singularities. And then, now the question is to construct some metric on F such that the Hermitian equation is respected, and such that this is a so-called orbifold metric. That is to say, the pullback with respect to this sort of maps extends continuously or smoothly to a metric of the vector bounded model that we have here locally. Okay, so we want the so-called orbifold version of theorem 1. That this is exactly what I will explain next. So let's consider an open subset W in omega. W is already fixed, right? So those are the bad guys, the singularities about which we don't know anything. And then we can do the following. As soon as this set is fixed, so we can construct a continuous function such that this omega orb is omega plus IDD bar phi has the following properties. So now in the complement of omega, so this metric is orbifold. So the pullback with respect to the local uniformization is quasi identical to the Euclidean metric. And then we can also impose that near W, so on a smaller subset here, we have that omega orb is the same as omega. Okay, so somehow we want this omega orb combines two different sort of geometry: the smooth one near W, and the singular orbifold one near outside. I mean, reasonably far from this set of bad singularities. Somehow you will see the technical reason for which we choose the metric like that. But I can tell you already that so if this set W is empty, then this means that X has quotient singularities, and then we can simply construct the orbifold metric on it. But then in general, we know nothing about the singularities here, and the best we could do is somehow something that interpolates between the two geometries. But somehow the behavior of these two metrics, this guy here and this guy here, it's very different. It's very violently different. So this creates many technical difficulties. And then in this context, we have the following. So so we have a compact Kahler space with log terminal singularities. So again, in this context, even if I will not tell you what this means, so that the hypotheses before are satisfied. And then we are given a stable Q sheaf on X orb. So Q sheaf means exactly that it has locally it has a structure of vector bundle near each point outside W. And then the same thing, we can construct a metric on F restricted to the smooth part with the following properties. It's smooth and satisfy the Hermitian equation here. Moreover, so we understand a little bit further the behavior of this HF. It has quotient singularities when restricted to the complement of omega. So somehow, when omega has this property, the solution of the Hermitian equation somehow it's automatic that it will be orbifold metric, so to speak. So the pullback with respect to this, it will be smooth. It extends smoothly across the singular loci. And then the same type of estimates as in term 1 hold true. Okay, so yes, the additional information is here, right? So in the complement of omega, we get nice Hermitian metric, and which has orbifold singularity, so to speak. And then we have the same type of estimates. Now, just a few words about the proof. It goes as follows. In the first place, because of this KLT or log terminal singularity condition, the following volume element is in LP for some P bigger than 1 on the desingularization of X. And then in this context, we know that we have a very, very strong results about the behavior of the solution of Monge-Ampere equation. So because of that, so we can use the Monge-Ampere estimates in order to approximate this metric with smooth ones. And then the entropy would be uniformly bounded by the way we choose the right-hand side here. And then use again the GPS results in order to take limits as we did before. Now this is somehow, this doesn't say much about the real difficulties, but somehow the outline of the proof is simply here. And the fact that these two metrics are very, very different is a main, somehow the main difficulties in analyzing the family of Monge-Ampere equations that we will use in order to approximate this metric to make it smooth, right? Because this omega odd is not smooth, right? It's like this. Fine. Now let's move to the Bogomolov-Giesecke inequality, which was somehow the motivation of all this. So we have X and F as in theorem 3. So that is to say, X has log terminal singularities, and then F respects this log terminal is a Q vector bound or Q sheaves, as we call it. And then now what we can do is to use this metric to define the Chern-Weil representatives for the Chern classes of F, right, for each K. Of course, only on X0. So this would give the representative of the so-called orbifold Chern classes of F, right? Because this metric has orbifold singularities in a complement of omega, of the open subsets, which includes the bed singularities. And then the main questions are, well, what are the numerical properties of this? So this one is the same as the quantity which appears in the Kobayashi-Lübke inequality. And ideally, we would like to prove that that inequality still holds. But then the problem is that, of course, this is only defined on X0. Now, what is relatively easy to see is that if we simply look at the analog quantity for the desingularization of F, this sort of inequality holds true. So we simply proceed by approximation. But then even if E is the pullback of F modulo torsion, this quantity here is very different from what we get at this level. If we compute directly on X, that's the main somehow source of difficulty. Now, I said that some people in birational geometry are never happy, and that's true. But what I meant is that the inequality which is somehow relevant for them is the one here. So the conjecture by Campana, Höring, and Pettener was the following. Now assume that we have a threefold. We have a dimension of X is 3, and then the set of singularities for which we know nothing is like a finite set of points. And then consider some function, let's say theta, for which this one form, so omega plus the Hessian of theta vanishes near W. Then this omega theta here, so this integral makes perfectly sense. And the conjecture was that this is semi-positive, right? So this was the analog of the Bogomolov-Giesecke inequality, or so the analog of Kobayashi-Lübke in this context. Okay, so somehow it's very looks very innocent because we put here IDD bar of some function, so Stokes should do it, but because of the singularities, it's not that simple, right? So now let's make some comment about this. So in the first place, what's the motivation of this result is that is my former colleague, Thomas Peternel, somehow he has a long-term project of implementing a minimal model program in the Kahler setting. And this is relevant in that context. Now, if X is projective, how people prove this? Well, is that, like I said, here we have a finitely set of points. So if we take a generic complete intersection, well, then we end up with a surface here which only has quotient singularities. Quotient singularities, we know how to deal with them. Okay, so in the projective case, hyperplane section is very useful and important technique. And then this inequality is the analog of Kobayashi-Lübke in the case, somehow in the quotient singularity case. Now, if the dimension of the singularities is 0, or if X admits a so-called partial resolution of singularities, then we showed with the many authors that this holds true here. But of course, so partial resolution of singularities means that we get some map from X hat to X, which is biholomorphic outside this set of points. Okay. So we somehow keep the quotient singularities, and the total space is supposed to be supposed to have at most quotient singularities. Okay, that would be partial resolution here. Now, in the meantime, Wenkauer Wu claimed the existence of such a partial resolution. So somehow this gives one possible solution to this problem. Of course, we prefer our solution. So in a recent work with Henri, so we established the following result, namely that this conjecture is true. So now to end my talk, I will say a few words about the proof of this. Now, somehow the key ingredient here, once again, is that this regular part of X endowed with orbifold metric admits a so-called green function, which is the one that the function that you know. But moreover, it is in this space in the W1 1 plus delta, and this is exactly the work of these people plus epsilon plus some additional work in it. And then somehow, so recall that the situation W here is a finite set of points, and then this omega is open subset containing them, and then outside omega we know everything about the objects that we have at hand. But of course, the difficulty is here, as you will see in a moment. And then somehow the main steps of the proof are the following. So this metric that we construct, the HF, the Hermite-Einstein metric on F, has the following property is that if we are giving ourselves a set V, which is contained in the orbifold locus, then our metric HF is somehow comparable with the orbifold metric on F. Okay, so even if the metric itself, omega theta, does not have orbifold singularities anymore, but at least at the C0 level, HF does the trick. It behaves as it should. So it's C0 close to orbifold metric, the complement of the points. This is just due to the fact that well, we have this metric satisfies the Hermitian equation that HF is a Q vector bundle, and most importantly, that's the estimates that we get for this metric when we get closer to the singular loci. And then somehow the heart of the matter is to prove that this so-called discriminant, which was on the slide before, is closed. That is to say, so when we integrate over the regular part, this one, which was C2 squared minus some C2 minus some constant times C1 squared, we integrate this against the d bar alpha, we get 0, provided that alpha has these properties, so that the norm of alpha plus d bar alpha is the subnorm is bounded. Okay, so it's in this sense closed, right? So again, so here this integral makes perfectly sense if you want. On x regular, HF is smooth, but then of course this is not closed space, and then yeah. So like I said, this follows from this inequality plus a few other things. But yeah, so if you I imagine that this is somehow hard to believe because this is order 0. This here involves two derivatives, but somehow what comes into the picture is the fact that we have L2 bounds for the curvature. Okay, that's somehow the point. And then the rest of the proof, like I said, is routine here. Now let's see, why do we bother to twist our metric to have it orbifold here, smooth here? So the quantity we have to evaluate is this one, right? We said that we take phi, which vanishes near in such a way that this object vanishes near our bed points. So then we can do the following. So evaluating this involves, if you want, two type of terms. One is chi epsilon times this, where we replace the metric here with the orbifold one. And the other one is chi epsilon of the discriminant times the Hessian of this sort of. So this is somehow a linear combination between the potential of the metric near the point and the orbifold potential, right? And theta is the cutoff function. And chi epsilon is a family of truncation functions converging to the identity of x minus our set of points. Okay. Now, what we have here is that luckily the Kobayashi-Lupke inequality is the pointwise one. So as soon as you have the Hermite-Einstein condition satisfied, then that inequality holds at each point. So then this one is positive for free, so to speak, right? Just because of the Hermite-Einstein condition. Now we have to get rid of the DDC of this function, and this is exactly where the second point before comes into the picture, because somehow we can integrate by parts because this is supported outside the set W. And then so now why does this integral converges to 0? So here the difficulty of the matter is that this discriminant is only in L1. Okay, it involves the coefficients of the curvature square, and that's just L1, right? So here better be L infinity if it goes to 0. So now the choice of the metric is exactly because, so as epsilon is small, so the support of this you're really concentrated near the points. So this one is out because theta is 1 there. So you only have to deal with the d bar of the phi p, which looks like that. So somehow this one explodes as epsilon goes to 0, but is compensated by the derivative of this, right? So when you take one derivative, you get of z, and then the two compensate each other. So, and the support of the integral is on smaller and smaller sets, and this is why it converges to 0. Okay, so now the last click is somehow very suited to our chair lady. So let's see now here. Thank you for the invitation.
I'm not sure that I can read all German letters. It's not common skill anymore. Thank you so much for the nice
Thank you.
talk. Is there any questions? Are there any questions? Projector, can you explain why this is so a crucial conjecture in this impedance program? Or
Yeah,
what do you explain?
So somehow very vaguely what is happening is that in dimension 3, there is this so-called abundance conjecture. For the abundance conjecture, this inequality plays a crucial role there. So somehow we want to prove that C2 of some vector boundary is so-called positive, and then the positivity of that is used in this manner. Okay, so that's how it comes into the picture via the positivity of C2. The proof of Kawamata and Yaoka in the projective case, and then these people somehow use many techniques from projective case, and then the crucial inequality is here. But then the hyperplane technique, slicing with the hyperplane in the projective case, is out in the Kahler situation. So yeah. So we are the positivity of C2. Yeah.
Oh, thank you. Any other questions? No. If that's not the case, we will continue 9:45 with Futaki's talk. I'd like to speak again.